Instrument calibration is key to producing products that meet specifications. The safe operation of measurement and control loops depends on instruments that supply accurate, reliable readings. Instruments are calibrated using conditions that simulate the actual process parameters in which they operate. Proper setup for instrument calibration helps to ensure that instrument errors are detected so that appropriate adjustments can be made. In this program, we'll look at instruments used to measure two kinds of process variables, flow and level. We'll see that although these instruments may operate differently, they are calibrated following the same basic principles. Instrument calibration should include setting up with the appropriate input and output standards, applying test inputs at several points in the instrument range, identifying the errors revealed by the tests, and finally, adjusting the instrument to correct the errors. The measurement of flow is an integral part of virtually every process. Depending on the application, one of several instruments can be used to measure flow. Effective calibration depends on understanding how instruments actually function in the loop and applying this information to the procedure. Differential pressure transmitters are often used in conjunction with differential producers, like orifice plates and venturi tubes, to measure fluid flow. The flow of conductive liquids and fluids that contain solids or particulate matter are typically measured by magnetic flow meters. A vortex shedding flow meter can also be used to measure fluid flow. And mass flow meters, like the smart mass flow meter here, can directly measure the mass flow of gas, liquid, or steam. Now, let's look more closely at one of the many methods used to measure flow, the differential pressure transmitter. Differential pressure is a way to measure flow inferentially. As flow increases, the differential pressure also increases. And when flow decreases, the differential pressure also decreases. The transmitter measures the change in differential pressure caused by a change in flow rate. An orifice plate is often used to restrict the fluid flow. This restriction creates a pressure drop that can be converted to flow rate. The orifice plate is placed in the pipe in which the liquid travels. As the fluid passes through an orifice plate, static pressure changes to kinetic energy in the form of velocity. The differential pressure transmitter measures the pressure drop created by this change. The amount of pressure drop produced depends on the volumetric flow rate. The differential pressure transmitter measures pressure at two different points, upstream and downstream. The differential pressure reading is the pressure drop across the restriction. Differential pressure, then, is the difference between the higher pressure or upstream reading and the lower pressure or downstream reading. Accurate flow measurements depend on properly calibrated instruments. When a differential pressure transmitter is properly calibrated, its output accurately represents its input. Now, let's see how a differential pressure transmitter is calibrated. Remember, the calibration setup should simulate the process conditions of the instrument under test. It's important that the instrument under test be mounted in the same position it's used in the field. An appropriate input standard must be used, since the differential pressure is usually measured in inches of water. A low-pressure calibrator can both furnish and measure the input pressure. A milliammeter is an appropriate output standard to measure the transmitter's output. Now that we've determined the input and output standards for the calibration setup, let's see how to connect them. We'll make the pressure connections first. This connection point is used to connect the transmitter to the pressure calibrator. According to the manufacturer's instructions for this calibrator, the transmitter should be connected to the P1 output port on the pressure calibrator. The pressure calibrator also needs 30 psi supply air in order to produce an output. The output from the pressure calibrator is connected to the high-pressure port on the transmitter to provide input pressure. The low-pressure port should be vented to atmosphere. This provides a reference point for the differential pressure measurement. To measure the transmitter output, a milliammeter is connected to the transmitter, and a 24-volt power supply is connected in series with the transmitter and milliammeter. Typically, inputs at these percentages of span are used as test points. The input range of the pressure calibrator is 0 to 50 inches. So, the first input value at 10% of span is 5 inches of water. The second input is 15 inches, and so on. The test points, the corresponding input values, and ideal output values can be determined from the instrument's range. Let's look at the readings for the upscale check. The first input value to the transmitter is 5 inches of water. The corresponding output is 5.3 milliamps. At 15 inches of water, the output is 7.5 milliamps. At 50% of span, or 25 inches of water, the output is 9.7 milliamps. Now, with 35 inches of water input, the output is 11.9 milliamps. And the last reliable input value at 90% of span has a corresponding output of 14.1 milliamps. A downscale check should also be performed to check for hysteresis. Hysteresis is an instrument error that's indicated by the offset between the reading for an upscale and downscale check. Often, the data from an instrument test is recorded on a calibration data sheet to help identify instrument errors. These readings are the result of the upscale and downscale check. The readings here indicate both a zero shift and a span error. Typically, when an instrument is calibrated, the zero is adjusted first. That's because to adjust span, you need an accurate base point, or zero. Zero should be adjusted so that for a 10% input, a 10% output is displayed. Once zero has been adjusted, span should also be adjusted. Since zero and span frequently interact, after one of these errors has been corrected, the other may require readjustment. A 5-point check will verify the accuracy of the calibration. Once you understand how an instrument operates, calibration isn't difficult. For example, flow rate is the square root of the calculated pressure drop across a restriction. Differential pressure transmitters may include an integral square root extractor, which converts differential pressure into flow rate. Remember, flow rate is the square root of the calculated pressure drop across a restriction. Integral square root extractors are part of some transmitters. If a square root extractor is not part of the transmitter circuitry, a separate square root extractor may be installed in the output signal loop. The installed square root extractor must also be calibrated for the loop to perform within specifications. Again, the setup for the calibration should simulate the process conditions. In the loop, the 4 to 20 milliamp output from the differential pressure transmitter provides the input to the square root extractor. So a milliammeter would be an appropriate input standard for the square root extractor in a calibration setup. Again, the output standard is a milliammeter. For this setup, the power for the output signal is supplied by the square root extractor. The calculations used to determine the test points for the square root extractor are complex. So typically, manufacturers' instructions, like the examples shown here, specify the input values and the expected outputs. The square root extractor has two different zero adjustments. Notice that the output values here do not follow the standard test points used in a 5-point check. That's because the square root of the input determines the output. In this example, the manufacturer specifies that span can be adjusted at 20 milliamps input. The other specified test points are 50 and 75% of span. The values displayed by these milliammeters indicate that the first zero has been properly adjusted, and these values show that the other zero is properly adjusted. When the input and output both display 20 milliamps, the span adjustment is correct for this instrument. Check the other two values after the zero and span adjustments are correct. Then make any other necessary readjustments. The remaining output checks for this square root extractor are performed at 50 and 75% of span. According to the manufacturer's instructions, these are specified input values and the required output values. If the actual outputs do not match the outputs stated by the manufacturer, further instrument adjustments may be required if the deviations are not within the accuracy specified by the manufacturer. In this segment, we've seen one method for measuring flow inferentially using a differential pressure transmitter. Here, accurate flow measurement relies on a properly calibrated transmitter. Sometimes differential pressure flow transmitters require a separate square root extractor located in the output signal line. This instrument, too, must be calibrated to help ensure that flow is measured properly. The input and output standards are chosen to simulate the actual process input and output signals used in the loop. Sometimes, test points may be specified by the manufacturer. Now, stop the tape to review what you've seen in this segment. In measurement and control loops where the process flow is a conductive liquid, magnetic flow meters can be used to measure flow. Conductive liquids are those which conduct electricity when a potential is applied. Magnetic flow meters are very useful in measuring slurry flow, such as fluids from sludge or paper stock. Let's take a look at how a magnetic flow meter operates. As fluid passes through the meter's magnetic field, the fluid acts as a conductor. The change in potential varies directly with the fluid velocity. This voltage is sensed by electrodes in the flow meter's walls. When the flow increases, the magnetic flow meter's output increases. And when the flow decreases, the magnetic flow meter's output also decreases. Now that we understand the operation of a magnetic flow meter, let's see how it's calibrated. First, the flow tube must be disconnected from the transmitter. A magnetic flow meter calibrator is used to simulate the signal provided by the electrodes in the flow tube. The operating voltage and frequency range of the calibrator must match those of the magnetic flow meter. Check the data plates on the calibrator and the magnetic flow meter to make sure that the values correspond. The magnetic flow calibrator has several functional features. The range switch is used to select the maximum output signal. The signal options include 5, 10, or 30 millivolts AC. This switch is used to set each output desired for a 5-point check. This magnetic flow meter calibrator has predetermined test points. Their millivolt values at 0, 25, 50, 75, and 100% of span. The input power indicators, when lit, show the value of calibrator input power. This calibrator will operate with either 118 or 236 volts AC nominal power. This switch is used to set the correct line voltage, as indicated by the lighted input power indicator. The switch can be set in two positions for correct phasing, either F for forward or R for reverse. The turns counting dial divides the maximum output set on the AC millivolt range switch in 1,000 equal increments. Each minor division of the dial has a value of 5, 10, or 30 millivolts. Since output is provided in milliamps, a milliamp meter is the appropriate output standard for this calibration setup. The power supply to the transmitter is 110 volts AC. Power to the calibrator is provided by the transmitter. The signal source from the calibrator is connected to the transmitter. The signal out of the transmitter is taken from the DC out terminals and is connected to the milliamp meter. It's important to observe the proper polarity when making this connection. To begin the calibration of a magnetic flow meter, calculate the input signal value. The input signal is equal to the upper range multiplied by the calibration factor by the phase band factor. All the figures you'll need are indicated on the instrument's data plate. Let's look at this one step at a time. The upper range value is multiplied by the calibration factor and the phase band factor. In this case, the input signal is 7.92 millivolts. Now, set the calibrator's range knob to select the maximum output signal. This is the smallest value, which includes the calibration input signal. For this example, then, the range knob should be set to 10 millivolts. Remember, the input signal is set through the turns counting dial. The outer portion of the dial indicates the whole number millivolt value. The inner portion indicates the decimal millivolt value. The turns counting dial here is properly set for the input signal value for this example. The outer dial is set on 7 and the inner dial at 92. Once the input standard is properly set, the instrument is ready to be tested. The magnetic flow meter calibrator here has predetermined test points. The first reading, taken at 0%, produces an output of 4.1 milliamps. At the 25% setting, the output produced is 8.1 milliamps. When the percent output switch is set at 50, the output produced is 12.1 milliamps. At the 75% setting, the output is 16.1 milliamps. The last reading in the upscale 5-point check is at 100%. The output produced is 20.1 milliamps. The output values produced during instrument calibration are typically recorded on a calibration datasheet. The datasheet shown here shows the upscale and downscale readings for the transmitter. A zero shift error is indicated because the actual output values are consistently higher than the outputs we'd expect.